we'll have, see this comes in with the same sign as this, so this would actually be 4 of these terms. We're mixing in x0 and x1 and so on. No matter what we do with the other terms, these are not going to drop out. This is not going to be the same as that, right? Any trick one can do to say that? The trick on this here is that the time, I mean obviously we know time really is something different from length. If we put a minus sign in front of this, then things actually become a little nicer. So if we have a minus sign, that was this term here, then we have a minus sign here, right? We have a minus sign here, nice. So then all the signs down here will change. This becomes a minus sign, this becomes a plus sign, this becomes a minus sign, right? Okay, then what we have, I can just read this down here. So then we have, what do we have under x1 squared? We have a gamma squared here. And what do we have here? Here we have another x1 squared with a minus beta squared. So minus gamma squared beta squared. Then we have, say from an x0 squared, let's write a minus x0 squared here because well, we kind of know what's happening. So minus x0 squared we have here, right? Minus minus, we have a minus beta squared gamma squared here. And we have a minus gamma squared x0 squared, minus gamma squared, right? And the mixing term x0 x1 minus 2 gamma squared beta x0 x1 plus 2 gamma squared beta x0 x1, right? Cancels out with that, right? So now we just need to figure out what is gamma squared 1 minus beta squared. What is that? Definition of gamma there. Gamma squared is 1 over 1 minus beta squared, right? So what is gamma squared times 1 minus beta squared?
3.
Second?
Gamma 3.
No. Gamma is square root of 1.
Oh, yeah, sorry, yeah, just gamma.
No. It's just 1, right? Gamma squared.
Yeah.
Gamma squared is 1 over 1 minus beta squared. So it's simply 1. That's what we have in front here. So this is minus x0 squared plus x squared. So what have we just shown is that if we incorporate time as the zero component, we know this normal length 3-vector product is no longer constant, it's no longer invariant. But what is invariant, write this down explicitly here. So with these, so it means that we have our x, what is it, x mu as x0, x1, x2, x3, with x0 in ct. Then we know that minus x0 squared plus x1 squared plus x2 plus x3 squared is constant or is invariant. So this is our new definition of our 4-vector dot product, scalar product. Let's call this our x dot x, or we can call this as x just with Einstein summation convention, that's what we mean. So we've defined a new 4-vector scalar product that essentially takes the role of the old scalar product in that whatever length this represents, that is the same no matter how you rotate it or boost it, no matter how fast it's moving. This thing will always be the same. Actual physical length in 3 dimensions will change, time will change, but this funny 4-vector product with the time coming in negative, that stays the same. So this is invariant, or specifically we call that Lorentz invariant. Lorentz invariant. So that means under any Lorentz transformation, any relativistic velocity transformation, this funny 4-vector scalar product stays the same. It's always the same value in any frame. That's what that means. Okay, so now this funny business with writing indices up and down will maybe start making a little bit of sense. So first of all, this kind of shows us that we are summing, because this is the same again, sum from 0 to 3, x, so mu equals 0 to 3, x mu. And the thing with moving this index down is now actually what gives us this minus 1. So we call x mu as contravariant indices, x mu as covariant, with the simple definition that for x0 we get a minus sign in there. For the others, it doesn't matter. 2 equals x2, x3 equals x. So this is really just a way to indicate this 4-vector product. If we take a 0 component of a vector in the scalar product, that means you always introduce that minus. So this way you get the minus time component squared. Okay. We can write this 4-vector product also in terms of some kind of a matrix. So if we have x dot x, we can also write this as a 4-vector x dot some matrix, let's call that G mu nu, times another 4-vector. So call this x mu G mu x mu. So write this as essentially so x0, x1, x2, x3 dot G times x0, x1, 2, x3. If you do that, this is of course another 4x4 matrix that we call the metric tensor. What are the entries then? If you want to write this in matrix form, matrix multiplication, to get this 4-vector scalar product out, then for the 0, 0 component you get minus 1, good. There's nothing else mixing in with x0, like 0, 0, 0, 0, and the others come in just on the diagonal with the plus. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. So this vector, this matrix, quite often that's also called eta mu nu. This is called also the Minkowski metric. So this is another way just to write this 4-vector scalar product. And particularly important is this because when you go on to masters and you take general relativity, then you'll start messing around with this so that it no longer looks so nice and simple. That suddenly you have all kinds of terms, sometimes even off-diagonal terms. And that's really what gives you all the mess in general relativity. In special relativity, everything is nice and flat, so you simply just have essentially in the 3 dimensions, nothing changed, but you get the time component in with a minus 1. Again, simply a way of writing things. All right, so now we can start visualizing things a little bit. First, we are working with coordinate systems all the time. Things obviously get a little bit weirder if now we have a 4th dimension that represents time, right? So let's forget about y and z components. We know they're not changing under transformation in x anyway. So let's just draw essentially a coordinate system where we have our x0 equals ct going up, and then let's just do only one space dimension, let's call that x. Then, there's of course critical lines. If we have light rays, say a light ray starts out from here, goes in positive or negative x, where would a ray of light that moves with the speed of light move in this diagram where we have time going up and space going in that direction? The light ray would go in what direction? 45 degrees up, right? So this is the light ray. So this is x equals ct, right? And when you visualize that, of course, if light goes in minus x direction, it will go in that direction. Right? And say if you want to visualize an extra, maybe a y direction, then of course this really becomes the cone, right? So you can rotate this around the time axis. So that's why these things then are called the light cones. So now, let's say you are actually looking at some kind of 2-dimensional vector starting out from here that goes exactly along this line. So let's say you have some vector A going in that direction. That's x. If that's the case, then x dot x. What is the 4-vector product of such a vector with itself? A 4-vector where you have x essentially as, so let's call it this light, L, it's L, it's light will have some kind of ct, but then the x component has exactly the same magnitude. Because it goes in the x direction just with the speed of light. What is the 4-vector product of that with itself? Will be minus x0 squared plus x1 squared, and well, 2 and 3 are 0 anyway, and that is 0, exactly. So, this is 0. It means any vector that has this kind of shape going in x and time at the same rate, that is called a light-like vector. So this xl is then called the light lag. Or going along a diagram in any direction, we often call a world line. We're going to consider any particles going in any velocity a long time. So this is essentially the world of a particle going. A particle that would go along this direction, so we call it a world light world line. So what is about if you have something x, say some kind of x, a particle that moves with less than the speed of light, but x particle for the less than speed of light. Where would such a particle go in this diagram? Try to color here. X particle. Where would the particle move in this diagram if it's exactly steeper up inside the light cone, right? So anything going in this direction, say this would be our x, any kind of massive particle that goes less than speed of light. What about this four-vector product with itself then? Is that 0, less than, or larger than 0? It's the same thing here. X naught is still ct. So minus ct squared plus, and well, but this is x1 squared, for example. Let's say we're going with a certain time here. We can write x1 as essentially vt, right? We're going a long time in x direction, then what we're going in x is just v times time plus vt squared. And is that larger or less than 0?
Yes.
Less than 0, right? That's negative. So if something has a four-vector product with itself that's less than 0, then that is something that physical particle can actually do. So this particle could really move along this line. So this is called a time-like world line. And finally, if we try to connect this point here to a point that's outside of the light cone, so let's call this xs with xs dot xs. We have that. And this would correspond, if we were actually going that way, would mean we have to go faster than speed of light. So our time component would suddenly be larger, so the space component would suddenly be larger than the time component. So it would be greater than 0. And obviously no physical particle can actually do that. That means in particular, there's no way that you can communicate in any way from this point to this point. See, the fastest way that you could go or send lights in any information would be along the light trajectory. Nothing travels faster than light, no information travels. So there's no way that this point would ever be in contact in any way with this point. You can't reach it physically, you can't send anything. So these 2 points are really separated in space, and there's no way that they can actually connect to each other. Of course, if something is stationary here and just goes in time, then at some time later we can communicate. But this point in space and time cannot communicate with that point in space and time. You can communicate with that point at a later time, of course, but not at the same space-time. That's what this means. So that's why a separation that has a four-vector product, dot product larger than 0, is then called a space-like. would lie of space-wide separation. And this kind of diagrams with space and time, these are called Minkowski diagrams. Actually with a line, not with a one. And they're a very simple concept, but actually quite useful, quite helpful to illustrate and to visualize some of the things, some of these paradoxes that we can discuss now. So let's, for example, go and look at a paradox called the twin paradox. I'm sure you've heard of it. Anybody? So this is X0, this is T, this is X. And we have our light cones. What does the twin paradox say? I'm pretty sure you've heard of it. What's it?
I can't remember perfectly, but I think it's about like if you have twins at a certain point at Earth, and they're at the same age, and one travels relativistically for, let's say, 2 years in his frame, and then comes back, and then eventually you should have a age difference. But then again, it depends on whose frame of reference you're looking at. Because for the one traveling away, it would seem that the time dilates that way for the other one. So it should create a paradox of who should be older afterwards.
Exactly, very good. So that we can illustrate. So if we have one of the twins staying on Earth, where will we go in this diagram then? Let's say x equals 0 is Earth. So where does he go if he just stays on Earth? Or just straight up, exactly. Straight up. So this is our twin A. And then we have twin B traveling obviously with less than speed of light, going this way. But what else does he have to do? What happens if he just keeps going and going and going? They'll never meet to compare their clocks. Right? So what does he have to do, or she? At some point, you will have to turn around so that they can come back and compare their clocks. What does that now mean for this observer? He has to, at some point, slow down, turn around, go back. Is that an inertial frame? It's an accelerated frame. So this means this is not an inertial frame, right? It means he will, in a little bit, probably after the break, he will indicate that the time that he experiences here will measure some kind of proper time, tau, on his own clock. But that's not a time in any kind of inertial frame. A time that you can compare this to an inertial frame is this one that stays stationary. So the answer will be very clear. This time will be less than the time that goes here. And after the break, we'll motivate this connection between this 4-vector scalar product length and the actual time. Okay, there's this other paradox that maybe you can illustrate this as well. This ladder and barn paradox. Anybody seen or read what that is? Yeah?
It's to do with the Lorentz contraction. So that's if you move, I think, relativistically at a speed, a ladder which usually wouldn't fit into a barn door, but then the length contraction would make it contract so that it would, at a relativistic speed, fit in.
Right.
And then, yeah.
Exactly.
Depends on kind of reference.
Yeah. So there's essentially there's a barn here that is 10 meters long, and then there's a ladder It's actually 20 meters long. So the idea being, if you're just going fast enough, so that you move with a Lorentz factor of 2, right? That means you have to move with square root of 3/4 of the speed of light. Figure it out. So if you do that, then, well, in the stationary frame of the barn, the ladder will be length contracted. So what you can do is, so have the rear door open, close that door at the same time that you open the back door. So there's a split second where the whole ladder fits in. But the problem is, if you're in the frame of the ladder, the barn actually moves with the same speed in the opposite direction. So the ladder will see the barn contracted. So how can the ladder fit it? Does anybody know the answer? Okay. The thing is, what we had discussed last time, simultaneity, what happens at the same time. So, first of all, what we can do, if we look at, so the barn frame, let's do this here, the barn frame obviously just moves straight, right? So this is the frame of the barn. The ladder is moving with a large speed in this direction, right? It's moving like that. So this is CT for the ladder, right? This is the time of the barn. So the ladder, well, if you are in the ladder, you're moving like this, but it feels like you're not going anywhere, because in the frame of the ladder, you're stationary. So this is effectively the time axis of the ladder, right? If you're sitting on the ladder and you say you're stationary, well, then you're only moving in time. And if you look at the form of these Lorentz transformations, what is the x-axis of the ladder? That is things that happen at the same time. So for the barn, everything that is horizontal effectively happens at the same time. For the ladder, you get this funny screwed x-axis here that has actually a time component in it. So the ladder sees things at the same time as they are on this axis. This is the x-axis for the ladder in this diagram. So you can here also see how time and space are essentially just mixed into each other and twisted into each other. So for the barn now, I don't have enough colors here, but anyway. So for the barn, say the barn is 10 meters long. But the ladder is nicely contracted and effectively moves. So the ladder has this length and effectively moves along. Right? So the ladder will look like that and just moves. And it's nicely length contracted. So for the ladder, however, well, it still kind of moves like that, but you see the time that it hits here first. So it hits the back door, actually happens much earlier than the time that it hits the rear door. So you see that, so this would then also be opening the back door and closing the rear door. If the ladder is effectively going, seeing things simultaneously here, so for the ladder, things happening at the same time like that. So what happens here actually happens much earlier than hitting the time axis here. So for the ladder, it means you open this door way before you close the rear door. So in fact, you open this door when only 5 meters of the ladder are through, then the whole length goes through, and when the whole ladder is through, then you close the ladder. So it's that concept of things not happening at the same time that saves you the paradox. So for the ladder, obviously the ladder is not in the barn completely at any given time. But it's okay because we're not closing and opening the doors at the same time. All right, I think this is a good breaking point. I'll get some coffee and tea.